Assalamualaikum and hi. Today our group is presenting our group project titled Reducing Drag Coefficient of an Ahmed Body using ANSYS Fluent. Okay, next one. Our group members consist of 3 members, Muhammad Bakir Sulaim Muhammad Ridin, Muhammad Azad Haiman bin Muhammad Haizul and Muhammad Hakim bin Muhammad Zaini. So for the introduction, first I will explain these statements. So why drags matter is because high drag coefficient increase fuel use and reduce vehicle performance, and the problem occurs when rear flow separation in vehicle Ahmed body creates turbulence and from drag and the challenges occurs when wind tunnel testing is costly for students. Need a simulation-based method to study and reduce drag. And this project aims to use ANSYS Fluent to simulate airflow and improve the Ahmed body design by reducing drag. For the problem statement, the key issue is the rear slant of the Ahmed body causes flow separation and turbulent wake. This results in high aerodynamics drag and low pressure recovery. The limitation of traditional method. Physical design changes and wind tunnel tests are expensive and time consuming, difficult for students to experiment and learn efficiently. For this, we need a solution. Identify a high drag zone, apply and test design changes virtually, and improve understanding of aerodynamic behavior. So for the objective, the main objective is to reduce the drag coefficient of Ahmed body using ANSYS Fluent CFD simulation. The specific goals is to understand aerodynamic flow behavior around the Ahmed body, learn and apply ANSYS Fluent for vehicle airflow simulation, perform a baseline analysis of drag and flow separation, design and test geometry modification to reduce drag, develop skills in simulation analysis and design optimization. So the scope of this project is study the Ahmed body and drag coefficient through research, learn and use ANSYS Fluent for CFD simulation, run a baseline simulation to get initial drag values, propose and apply design modification to reduce the drag, perform multiple simulation to refine and optimize result, analyze flow, pattern, velocity and pressure changes, focus on visually testing only and no physical prototypes. Next. So for the literature review, I explain why we study aerodynamics. So aerodynamic drag affects fuel efficiency, vehicle stability and performance. Ahmed body as a benchmark is developed Ahmed body at 1984 simplified model of vehicle use in aerodynamic studies, help analyze wake formation, flow separation and drag behavior. And we study used widely in CFD and wind tunnel experiment, ideal for testing aerodynamics improvement in control way. So Ahmed body is a simplified car shape developed by S.R. Ahmed, designed to study aerodynamic drag and flow behavior. The key feature is rear slant angle, usually at 25 degree, affects flow separation and wake size. Typically between 0.25 to 0.5 depending on geometry. And why it matters is because it helped researchers test changes like vortex generator, spoiler, diffuser, and easy to simulate and modify for CFD studies. CFD in aerodynamics analysis. So what is CFD? It is a computational fluid dynamics. Simulate airflow digitally and replace expensive wind tunnel tests. So why use CFD in this project? It is to visualize airflow, pressure, and vortice around the Ahmed body helps the test modification quickly and virtually. So, powerful CFD software for external simulation supports realizable Spala Almaraz turbulence model, good balance of accuracy and efficiency.
Literary review and summary. The Ahmed body is a trusted model for studying vehicle dynamic. It allows control testing of flow separation, weight zone, and drag. CFD tools like ANSYS Fluent provide a virtual environment to analyze and improve the designs. And combining simplified geometry and advanced simulation enables effective debt reduction strategy, also cost effective. Next, model setup overview. Simulation overview is created a 3D Ahmed body using CAD software, import using CATIA or SolidWorks. Also can use on ANSYS Workbench. Then imported the model into ANSYS Fluent for CFD analysis. Simulated airflow in a rectangle domain to mimic wind tunnel conditions. First, the main step. Next, the main step involve geometry preparation, mesh generation, boundary condition setup, and solver and fluid settings. The goal is to analyze and reduce that coefficient CD through virtual aerodynamic testing. Next, geometric preparation. In the model creation, a 3D Ahmed body was built using CAD software as they shown in the pink box. Dimension followed Ahmed et al. At 1984 to ensure accuracy. Simulation domain, the Ahmed body placed at the center of a rectangular domain. The domain size was selected to simulate wind tunnel condition and avoid boundary interference. The purpose is to ensure a realistic flow environment for analyzing aerodynamic performance. Next is mesh generation. Starter mesh created using the ANSYS meshing. It is focused on capturing critical flow regions around the Ahmed body. Key features is boundary layer refinement near the surface to resolve flow separation. Inflation layer added to improve accuracy in viscous sublayer and capture velocity gradient effectively. Mesh quality it is tuned for high aspect ratio without skewness to ensure stimulation accuracy and stability. It also have 60,000 elements in there to ensure most respectable result. Next, and the boundary condition. The velocity of inlet air is about 13.98 meter per second, and it is also represent a typical highway speed or tunnel speed. Outlet is 0 Pascal because it is simulated an open airflow environment, not the whole tunnel thing. And top and side wall is symmetry boundaries condition over artificial shear or constraint, just a solid rectangular block. Ahmed body surface is no slip wall to ensure zero velocity at solid surface for realism. Next. Okay, next is solver setting. The solver type we use is steady state pressure based solver suitable for external aerodynamic flow. The velocity formulation we use is absolute velocity, standard for airflow simulation. And the gravity is ignored because it's not relevant for horizontal vehicle flow. The turbulence model is realizable Spala Almaraz model selected for better accuracy in flow separation prediction, improved result over standard Spala Almaraz model that handles adverse pressure gradient well. Next. And fluid properties. Working fluid is air, model as an ideal gas because it all around us and in the tunnel because it's a car, not a submarine. And the reason is to allow for compressible effect at higher velocities. It defines properties with density calculated via ideal gas law with dynamic viscosity around 1.7894 and specific heat is about 1006.43 J/kgK. Environment, standard atmospheric condition is assumed. No storm, just standard.
Wizard baseline model. For the baseline Ahmed body simulation, were the coefficient measured at 0.365 match typical literature range between 0.25 to zero point 0.4. The flow behavior separation occur at Graceland. It generates vortices and large weight region. Mesh setup is 60,000 elements and refined near surface and weight zones for accuracy. Baseline baseline model for CFD analysis are for flow analysis, velocity contours show clear flow separation at Graceland, large weight region with low momentum flow. Pressure distribution, it is high pressure at the front and there is sharp pressure drop at the rear from drag. For the confidence info, the residuals uh, uh, 10 negative 4 after 400 iteration and drag coefficient stabilized at 0.365. The initial condition from the inlet velocity is 13.98 meter per second. Also, turbulence intensity 5%. Based on result in modified model, the modification applied vortex generation position at Graceland by 20-degree angle, have delay flow separation, also rear diffuser at stand lower rear section, add in pressure recovery. For the result, drag coefficient reduced to 0.312, also 40.5% improvement over baseline. For the flow behavior, it improved flow attachment, smaller and weaker weight region. Same for the mesh, same structure as baseline, extra refinement near vortex generators and diffuser. For the modified model, based on CFD analysis, velocity contours, it shows more attached flow and smaller weak zone and weaker vortex formation. For the pressure distribution, it's gradually pressure drop from front to rear. It has better pressure recovery, less form drag. Yeah. Also, converged behavior, the residual over 10 days before after 500 iteration. Also, simulation stop at 1000 iterations. For the result, drag coefficient reduced to 0.312. Also, confirm effectiveness of modifications. For model comparison, as we can see, the baseline model and modified model are different based on their CD, which is the modified model was lower by 14.5%. Also, it had better flow rate attachment, smaller and smoother weight, also improved pressure recovery. For the and the conclusion for it, design modification from vortex generator plus diffusers, it significantly enhanced aerodynamic performance. CFD effectiveness and limitation. The effectiveness of CFD based on ANSYS Fluent enable virtual aerodynamic testing, accurately predicted flow separation and pressure zones. Realizable Spallet-Almaraz model capture external flow behavior well, allowed for multiple design iteration without physical models. For limitations, no ground effect or wheel rotation included, steady state only, no transient flow analysis. Use simplified geometry, which is Ahmed body. Also, no crosswind or yaw angle effect considered. The recommendation is to use transient simulations and more realistic vehicle models, include moving ground and rotating wheel in future studies. For my conclusion, using ANSYS Fluent, the drag coefficient of Ahmed body was reduced from 0.365 to 0.312. Vortex generator and rear diffuser improved flow attachment and pressure recovery. The project demonstration how CFD can optimize vehicle aerodynamics in a cost-effective and educational way. And for management. Thanks to you, Tem, our lecturer, for guidance. And we are gratitude to the team member for collaborating and an effort. And we appreciate to all involved in supporting for the project. Thank you.